Okay, picture this. A satellite that cost millions, maybe even billions of dollars, is tumbling through space, totally out of control. It's hundreds, maybe thousands of miles away. You can't just send a mechanic up there, right? So, how do you figure out what's wrong? Well, today we're going to dive into a really fascinating new idea. What if we could train an AI to be a doctor for these 6 satellites?
It really all comes down to this one simple question. I mean, a satellite has to point somewhere very specific, whether it's at Earth to beam down data or at a distant star for science. So how in the world does it stay so perfectly still and pointed in the right direction in the middle of empty space?
Well, the answer comes down to this little piece of genius engineering, the reaction wheel. What you're looking at here is a pyramid setup of 4 of them, and these things are pretty much the unsung heroes of satellite stability. They are what lets a satellite aim with incredible precision.
So how do they work? It's actually kind of simple and brilliant. Think about an ice skater. You know how when they pull their arms in, they start spinning way faster? Reaction wheels use that exact same physics principle, conservation of angular momentum. You spin up a heavy wheel in one direction, and the entire satellite body rotates in the opposite direction. No fuel, no thrusters, just pure physics. It's awesome.
But, and this is a big but, here's the catch. If one of these wheels fails, if its motor glitches or it just seizes up, the consequences are, well, they're catastrophic. The satellite can lose its aim, it can't talk to us anymore, and it basically becomes a very, very expensive piece of space junk. The stakes are incredibly high. So this leads us right to the main problem. You've got a 6 satellite, but you can't touch it. You can't run tests on it in the lab, so how do you diagnose the problem from so far away? For a long time, engineers used what's called a model-based approach. They try to build this perfect mathematical blueprint of the satellite. The only problem is, real spacecraft are unbelievably complex, and those models are almost never perfect. So the new way, and this is what our source paper is all about, is data-driven. It's kind of like a doctor who doesn't need to see your personal blueprint. They can just look at your symptoms, your data, and figure out what's wrong.
And you can see here exactly why that old blueprint method is such a headache. Modern satellites are just too complex. You've got what's called high dimensionality, which just means there are tons of variables all interacting. You've got nonlinearity, where one tiny change can have a massive, unpredictable effect. And then there are just uncertainties you can't even measure. Trying to make a perfect model is, well, pretty much impossible. So the researchers behind this study had a pretty radical idea. They said, okay, instead of trying to build a perfect blueprint, let's just train an AI to be a remote diagnostics expert. Let's build an AI doctor. And they have this really methodical 4-step process. First, they couldn't just wait around for real satellites to break. So they created 80,000 digital simulations of both healthy satellites and sick ones. Then, from all that data, they pulled out over 60 different symptoms or features. Third, and this is key, they used an algorithm to figure out which of those symptoms were actually important and which were just noise. And finally, they fed that clean, refined data to a bunch of different AI models to see which one would graduate at the top of its class. And get this, after all that work in step 3, they found that out of more than 60 possible symptoms, the AI only needed to keep an eye on these 22 to make a super accurate diagnosis. And that's really important, because it means the AI can be lean, efficient, and actually run on the kind of limited computers you find on a real satellite. And right here, in the researchers' own words, you can see their main goal. They wanted to create a system that could, all on its own, autonomously, figure out which specific reaction wheel was failing. Not just that something was wrong, but exactly where the problem was. Of course, having a great idea on paper is one thing. You've got to prove it works. So to really see what their AI doctor was made of, the researchers put it through a series of really tough stress tests. They didn't just test it on one type of satellite design. They basically created 3 different obstacle courses for the AI, testing it on 3 of the most common ways that reaction wheels are set up. First up was this pyramid configuration. Now, what makes this one so tricky is its symmetry. A problem in one wheel can look almost identical to a problem in another wheel, which makes it a real challenge for the AI to tell them apart. Next was the standard 4-wheel setup. This is a super common design, and it usually includes a spare wheel for redundancy. So if one breaks, another one can help pick up the slack, but the AI still has to identify the right one that's broken. And finally, the simplest setup of the bunch, the 3 orthogonal configuration. Here, you've got one wheel for each axis, X, Y, and Z.
This makes failures a little more obvious to spot, so it was a good baseline to test to see if the AI had the basics down.
So, the moment of truth, how did it do? Well, for those sudden, total failures, the results were, frankly, amazing. The best model they tested, which is a type of AI called a random forest, was more than 96% accurate across the board. It even hit almost 99% on that standard setup. It could pinpoint the exact failing wheel almost perfectly. But, reality is messy. A wheel suddenly dying completely is one thing, but what about the more subtle problems? What about glitches that are temporary, that kind of come and go? And this is where the story takes a really interesting twist. When they tested the AI on these much trickier, more realistic, transient faults, look at that. The accuracy just plummeted. For the standard configuration, it went from almost 99% accuracy all the way down to just 24%. So what happened? Well, these glitches were so quick and subtle that the satellite's own control system would fix the problem before the AI doctor even had enough clean data to make a confident diagnosis. The system was masking its own symptoms. Now, even though that last result shows there's still work to be done, this research is pointing us toward a really exciting future. A future where we have truly smart spacecraft that can monitor themselves. This quote from the paper just nails why this is so important right now. We are launching more satellites than ever before, especially these smaller ones that don't always have all the expensive backup systems that the big ones do. We absolutely need smarter ways to keep them healthy and safe. So, what's the big takeaway here? Well, this whole data-driven approach means we get more autonomous satellites that can watch over themselves. It means more reliability, especially for those big constellations of small satellites. It also means lower costs because you don't have to spend a fortune developing a new mathematical model for every single mission. And maybe most importantly, you get faster diagnosis. The AI can find a problem in real time, right there on the spacecraft. Which really leaves us with one final, pretty mind-bending question. We've just seen an AI that can work as a doctor. With that kind of autonomous diagnosis, are we heading toward a future where spacecraft can not only find their own problems, but maybe, just maybe, fix them too? Could they actually become their own mechanics, millions of miles away from home?